Have you ever stopped and really thought about your refrigerator? Or your air conditioner? How does it actually make things cold? It can feel a little bit like magic, but it's really just some incredible, fascinating science. So let's get into it and explore the hidden world of how refrigeration really works.
So, let's start with the most basic question of all. How do you make something cold? It seems obvious, right? I mean, if you want to make a room warmer, you add heat from a heater. So, to make something colder, you just add cold, right? Well, actually, no. That's not how it works at all.
And here is the fundamental secret, the big idea behind all of this. You can't make cold. Cold isn't really a thing you can add to a space. It's just the absence of heat. So that means every single refrigerator, freezer, and AC unit out there isn't a cold maker. It's actually a heat mover. Its entire job is to grab heat from one place, like inside your fridge, and dump it somewhere else, like into your kitchen.
Okay, so if the name of the game is moving heat, what's actually doing all the heavy lifting? Well, that brings us to the real heroes of this story, these very special substances, both liquids and gases, that we call refrigerants. The official textbook definition is pretty simple. It's just the stuff, the working fluid that's constantly cycling through all those pipes in a cooling system. Its whole purpose in life is to absorb a bunch of heat in one spot and then release it in another.
Now, it turns out engineers have two main ways to use these refrigerants. The first is with primary refrigerants. These are the workhorses. They do the job directly. They're the ones inside your fridge absorbing the heat. But in really huge systems, you'll often see secondary refrigerants. Think of them like a middleman. Something like a salty brine is first chilled by the primary system, and then that cold brine is pumped around to cool everything else down.
So let's follow a primary refrigerant on its journey. It all starts in the evaporator, those coils inside your fridge. Here, the cold liquid refrigerant absorbs heat and boils, turning into a low-pressure gas. Next, that gas gets sucked into the compressor. This is the heart of the system. It squeezes the gas, which makes it super hot and high pressure. From there, it flows to the condenser coils on the back of your fridge, where it dumps all that heat out into your kitchen, turning back into a liquid. And for the grand finale, it goes through a tiny expansion valve, which makes it incredibly cold, and it's ready to start the whole cycle all over again.
And it's not just one magic chemical that does all this. Engineers have this huge library, a whole zoo of different chemicals they can pick from, and each one has its own special talents.
Let's make this real for a second. You've probably seen a can that looks just like this if you've ever been to an auto parts store. This stuff is R134A, a really common refrigerant. For a long time, this was the go-to chemical for car air conditioning. It's a perfect example of picking exactly the right chemical for a very specific job.
And that's just scratching the surface. You've got the halocarbons, like that R134A we just saw. But then you have a totally different class, inorganic compounds. For instance, R717, which, believe it or not, is just plain old ammonia, is an absolute beast for huge industrial freezers. And then there's R744. That's just carbon dioxide. You see it all the time now in supermarket freezers because it's much better for the environment. Different jobs, different heroes.
Okay, so with this whole family of chemicals to choose from, how on earth do engineers know which one to pick? I mean, what's right for your car's AC is totally different from what's right for a giant warehouse. Well, it turns out they have a very specific wish list of properties they're looking for.
First and most important are the thermodynamic properties, how it behaves with heat. You absolutely need a low boiling point, so it can easily flash into a gas and soak up heat, even when it's already freezing cold. And you want a high latent heat of vaporization, which is really just a fancy way of saying it can absorb a ton of heat energy. It's all about efficiency.
But then you've got the real-world practical stuff. How much does it cost? Because that's going to affect the price of the appliance. Is it toxic? Is it flammable? I mean, you definitely don't want your air conditioner to be a safety hazard. Can you easily tell if it's leaking? These physical properties are absolutely crucial for making a product that's both safe and reliable.
And finally, you have to think about its chemical nature. You need something that's super stable, something that's not going to break down or corrode the pipes after being squeezed and expanded millions of times over 20 years. So you see, the perfect refrigerant doesn't exist. It's always a careful balancing act between all these different factors.
So, once we've picked our hero, the right refrigerant for the job, we need a battle plan. We have to figure out exactly how much heat we're up against. In engineering, this is called calculating the cooling load.
This right here is maybe the most critical question an engineer has to answer. Because think about it. If you get this wrong and underestimate the heat, the system will never get the space cold enough.
But if you overestimate it, you're just building a system that's way too big and wastes a ton of energy and money. You have to nail it.
So how do they do it? Well, they create something that's basically a heat budget. Let's use this Apple storage room as our example. To figure out the cooling load, they have to meticulously account for every single way that heat can get into this room or be created inside it.
So what's in the budget? Well, you've got the obvious stuff, right? Heat leaking in through the walls, the ceiling, the floor. Then there's the product itself. All those apples are warm when they arrive. You've got heat from the lights, from any machinery, even from the people working in there. And of course, every time that door swings open, warm air rushes in. But here's the crazy part. The apples themselves are alive. They're respiring, and that process actually generates heat. You have to add everything up.
After they have painstakingly calculated every one of those heat sources, the walls, the product, the people, the lights, they add it all together. They sum it all up, add a little safety factor just in case, and they get one single critical number, the total cooling load. That number tells them everything. It determines how big the compressor needs to be, how much refrigerant they need. The design of the entire system is based on that number.
So you see, what feels to us like just making something cold is actually this incredibly detailed, meticulously engineered system. It's like a complex puzzle with two huge pieces that have to fit together absolutely perfectly.
On one hand, you have the materials science, combing through that whole zoo of chemicals to find the perfect refrigerant from the wish list. And on the other hand, you have the math, building that precise heat budget to know exactly how much work needs to be done. Putting those two together, well, that's what modern refrigeration is. It's a true masterclass in detail.
And that really brings us to a final, really important thought. In a world that's getting warmer, the science of moving heat is more critical than it's ever been. The big challenge for engineers today and tomorrow is to find new refrigerants and design new systems that aren't just powerful and safe, but that are also sustainable for our planet. So, the question we're left with is, how will we engineer the future of cold?